right, let's do some examples working with normal distributions in general. And we're going to have to do some conversion here so we can answer this using the standard normal table that we have. So in this example, let's say that we're given x has a normal distribution. X has a normal distribution with mu, a mean of 50, and sigma equaling 10, standard deviation of 10. Let's find the probability that x is between 45 and 62. Let's find the probability that x is between 45 and 62. Okay. All right, so using what we have above here, we know we can convert this to a standard normal random variable question, but we need to know what our bounds are. So here, you look at this, 45 is our x1 value, and 62 would be our x2 value if we relate to the result we have on the screen above. So let's find the associated z values here. X1 minus mu over sigma. X1 here is 45, so this is 45 minus mu. The mean we're given is 50, and we're given a standard deviation of 10. So this is, what's the difference on top? That is negative 5 over 10. So this is minus 1/2, or negative 0.5. And I'll write this as a decimal because remember that the table is organized as a decimal to 2 places. So we're going to look up negative 0.5 in the table probably. And then what's the upper bound here? What is our upper bound? Let's say z2. So now this is x2 minus mu over sigma. x2 then is 62. So 62 minus 50 over 10. That is 12 tenths. As a decimal, that is 1.20. 1.20 or just 1.2. Okay, so here we go then. The probability that x is between 45 and 62 then is equivalent to the probability that a standard normal random variable z is between negative 0.5 and 1.2. And so now we just have to answer this standard normal random variable question. What the area between 1.2 and 0.5. This stage, we should be pretty comfortable, hopefully, working with the standard normal table. Here's 1.2. Here's negative 0.5. So I'm going to compute all of the area and subtract off the area that I don't want to be left with just this area. So I want that area. So we're going to do the probability that z is less than 1.2. And we need to subtract the probability that z is less than negative 0.5. So let's go ahead and take a look at what these values are in the table. 1.2. Where's our 1.2? This is just 1.20. So that's 0.8849. 0.8849. And then while we're at it, we're also going to need negative 0.5. So we've got 0.8849. And then what's the negative 0.5? So that's negative 0.50 is 0.3085. Okay, so let's copy this down over here. So this is equal to 0.8849 and then subtracting 0.3085. And we run the arithmetic there through a calculator, and we've got 0.5764. 0.5764. All right. So normal distribution questions. When the mean and standard deviation differ from the standard normal distribution, we just convert it to a standard normal distribution question. One of the reasons why we are really focused earlier on getting familiar working with the normal table and answering questions like this is because a lot of the times things boil down to solving that specific problem. Let's do another example. Let's suppose x is normal with mean 40 and standard deviation 6. Find the value of x that has, let's do 2 parts here. Part A, 45% of the area to the left. 45% of the area to the left. 45% of the area to the left. Okay. Now, we've been able to answer questions like this with the standard normal distribution. So we want to be able to approach this in a similar fashion, right? So let's just think about this. If we had a standard normal distribution, if we had a standard normal distribution, and we wanted the area, we wanted 45% of the area to the left, we could find that value, right? That would be finding the k value, so, and to the left. So probability that z is less than k equals 45%, or 0.45. We could look up that k value in the table. We'd find k equals what? Where's 0.45 going to be in the table here? 0.45. Now remember, 0.45 is the probability, so we're looking at the entries in the table here. So 0.450 is about here. That's our closest value. 0.450, that's pretty close. So it's about negative 0.1, what is that? 2? Negative 0.12. Negative 0.12. Probably something like negative 0.122 or 123. This is too small, but it's a bit closer to this. So for now, I'll just say it's about negative 0.12. That's our closest value. Is that our closest value? Let me take a closer look here. 0.450. This is 22 10,000ths away. This is only 17. This is actually closer to 0.450 than that is. So I would maybe take the second value. This is actually closer, right? 0.4483 is actually closer to 0.45 than 0.4522. So that's negative 0.1, negative 0.13. Let's go with that. Negative 0.13. Okay, there we go. So what can we do here? But this is for a standard normal distribution. We don't have a standard normal distribution. But we always have a relationship between a standard normal distribution. Remember that your bound in a standard normal distribution is equal to x minus mu over sigma. So in this case, we could convert to the x value by substituting this in for z. And we have a mean of 40 and a standard deviation of 6. So let's use that relationship. So when z is negative 0.13, negative 0.13 equals x minus 40 over 6. And now you can solve for x. Now we can solve for x here, right? We can multiply by 6. Multiply it by 6, and then we're going to need to add 40 to solve for x there. So we should find then, once we do the arithmetic here, x is about, if I round that off, that's about, I've got 39.22. 39.22 for that. Okay, 39.22. So we can convert back and forth here. Again, this is the fundamental relationship that we're trying to become familiar with. Let's take another stance or another question with the similar distribution. Let's say, so that was 45% of the area to the left. Let's go 14% of the area to the right. 14% of the area to the right. 14% of the area to the right. Area to the right. Okay, so think about 14% of the area to the right here. Maybe we'll draw a picture if I need to. And I'm going to start again by thinking about this in this standard normal sense. So I've got a mean centered at 0 here. 14% of the area to the right. So there's going to be some value for z here. That's going to leave me this area to the right of this. That's going to be 14%. That means the area to the left then, that would mean what, all of this area right here. What's the opposite there? 1 minus 14. That area would be 86%, right? 86% of the area to the left. Oop. Losing my screen here. 86% of the area to the left. Okay, so we can look up that value in the table. What value of z in the standard normal distribution is going to give us 86% of the area to the left. Let's go ahead and take a look. 86% of the area to the left. Where is 0.860? Right about here. Right about there. That is very close. I've got a low battery here. Let's see if we can't wrap this up. What is that? 1.08. So 1.08. So we know that the probability that z is less than 1.08 is equal to 0.86. Okay, I just plugged in my charger here, so that shouldn't fix anything here. So let me see where we left off. We're looking for 14% of the area to the right. For x, that follows a distribution with a mean of 40 and standard deviation of 6. So we do know that the associated value of z that would give us 14% of the area to the right would be 1.08. 1.08. So using this value here, we should be able to see then, let's see, 1.08 equals x minus, the mean here was 40 over sigma, which is 6. And we can solve for x. And what do we share? 1.08 times 6 plus 40 is 46.48. There we go. Looks good. 46.48. Okay. Nice. I like it. So that's how we can work with converting back and forth between a normal distribution that is not standard and one that is standard, right? We're really making use of this relationship right there. Okay. One last example just for kicks. Short one here. If, let's say, a set of observations are normally distributed, what percentage of them differ from the mean by more than 2 standard deviations? Approximately. What percentage differ from the mean by more than 2 standard deviations? 2 sigma. Okay. Let's think about what we're asking here. If a set of observations are normally distributed, what percentage differ from the mean by more than 2 sigma? We don't even really know what normal distributions we're talking about. We don't know the exact mean, and we don't even know the exact standard deviation, right? So in general, just sort of think about what this is. You're looking for a probability. If they differ from the mean by more than 2 sigma. Differ from the mean by more than 2 sigma. So we're actually, if we draw a picture here. So maybe here's sigma and then 2 sigma. Differ from the mean by more than 2 sigma. So we'd be looking for this probability. And if this is negative sigma and this is negative 2 sigma, in addition to that, we'd want this area as well, right? We'd want that area as well. Okay. So how can we calculate this? By symmetry, right? We should at least agree by symmetry that these areas are the same. These areas are the same. So we want twice the probability that a random variable, let's say x, is less than negative 2 sigma. Twice the probability that a random variable x is less than negative 2 sigma. Now think about if you're going to try to start converting this to a standard normal random variable question. Z is equal to x minus mu over sigma. Okay. Set of observations is normally distributed. What percentage differ from the mean by more than 2 sigma? Differ from the mean by more than 2 sigma. Does it really matter what the distribution of x is? If it's well, you got to be careful with this here. Let's think about what these values actually are. I guess I should be very careful with my notation here. Because I'm going to say that this value right here is where the mean is, right? That's where x is equal to mu. Now, if the mean is 0, then this is actually sigma units away. But we should be careful because if the mean is not 0, let's say the mean is 5 and it has a standard deviation of 10, right? Well, then this is not 10, but that is 5 plus 10, right? So these are all actually mu plus sigma, and this is actually mu plus 2 sigma. So this would be mu minus 2 sigma. So we should be careful here. If it's going to differ from the mean, we want to be mu minus 2 sigma away from the mean, right? That's the actual x value we'd take on. That's the actual x value. So when we go to convert this, x is mu minus 2 sigma. So this is mu minus 2 sigma. That goes in for x. Then it's minus mu over sigma. And so here's I sort of got ahead of myself mentally. The mu's cancel, and you're left with negative 2 sigma over sigma. Sigmas cancel, and so you're left with negative 2. So it's for z equaling negative 2. That is 2 standard deviations away on the standard normal table, right? Because the standard normal distribution has a standard deviation of 1. So this is equal to twice the probability that z is less than negative 2.0. So then we just need to go on the table and look up negative 2. And here we go. Negative 2.0. Right there. 0.0228. And then we're going to go ahead and double that. We're going to go ahead and double that. Twice 0.0228. And that is 0.0456. About 4.56% differ from the mean by more than 2 sigma. So kind of the takeaway about this that I sort of want us to think about is in regards to being away from the mean, right? And you're asking about standard deviations, it doesn't matter what the spread is or what the actual standard deviation is because your difference is relative already to how spread out you are. So if I have a normal distribution that has a standard deviation of 5, and I have a normal distribution that has a standard deviation of 10, it's still the same likelihood that you're more than 2 standard deviations away from the mean, whatever that is. Okay? So in this case, that's about 0.456. It's the same thing as a normal distribution being, 2 points away. So I'll leave it with that there for the end of this one, okay? Next up, we're going to do some more normal distribution questions. We'll start throwing some words into the mix and look at some application questions. Ultimately, though, it's going to end up with us looking up some values in the standard normal table. We'll see you in the next videos.